Now let's talk about types of errors when evaluating statistical hypotheses. Type 1 error is incorrectly stating that there is an effect or difference when none exists in reality. In other words, type 1 error occurs when the experimental or alternative hypothesis is mistakenly accepted and the null hypothesis rejected, when in reality the null hypothesis is correct. The probability of making a type 1 error alpha is equal to the p-value in a study. Hopefully the concept of a p-value is familiar to you. At the very least, you should know that the p-value is typically judged against a preset level of significance, usually 0.05 in most studies. If p is less than 0.05, this means there is less than a 5% chance that the data will mistakenly show an effect or difference when none exists. Thinking about what we've already discussed, what is another way to describe type 1 error? Type 1 error is also the false positive error. A real-life example of type 1 error is convicting an innocent person of a crime. You are rejecting the null hypothesis that the man is innocent, and you are accepting the alternative hypothesis that he committed a crime, when in fact the null hypothesis is true. Type 2 error is stating that there is not an effect or difference when one exists in reality. In other words, type 2 error occurs when you fail to reject the null hypothesis, when in fact the null hypothesis is false. The probability of making a type 2 error is denoted by the Greek letter beta. Thinking about what we've already discussed, what is another way to describe type 2 error? Type 2 error is also the false negative error. A real-life example of type 2 error is setting a guilty man free. You are accepting the null hypothesis that the man is innocent and rejecting the alternative hypothesis that the man is guilty of committing the crime, when in fact the null hypothesis is false. The concept of power is very important in study design. Power is the probability of rejecting the null hypothesis when it is in fact false, or the likelihood of finding a difference if in fact one exists. Continuing with our example, one could say that the power of the judicial system is a likelihood of determining a defendant guilty when he or she is in fact guilty. Hence, a powerful study is one that has a high likelihood of detecting an effect or difference when one is present. The mathematical definition of power is 1 minus beta, which means that power can also be thought of as the probability of not making a type 2 error. For example, let's say you are flipping a coin. The null hypothesis is that it is a fair coin with equal probability of coming up heads or tails, and the alternative hypothesis is that heads is favored. If you only flip the coin 10 times, even if 6 are heads and 4 are tails, you don't have enough statistical significance to reject your null hypothesis because the power of your experiment is too low. If instead you flipped the coin 1,000 times and got 600 heads and 400 tails, now you have enough power to reject the null hypothesis and conclude that this coin favors heads. Power depends on several different factors. First, if you increase the sample size, you increase the power of a study. You can remember this with the aphorism, "There's power in numbers." Similarly, if the spread in the data decreases, you are more likely to detect a difference if there is one, and therefore the power of your study increases. Second, if you increase the significance level, or probability of type 1 error alpha, you increase the power. There's a trade-off between type 1 error alpha and type 2 error beta. So if you're willing to accept a higher probability of type 1 error, you reduce your probability for type 2 error. Since power is defined as 1 minus type 2 error, this effectively increases power. Finally, as the difference in the mean values between groups, or the size of the expected effect increases, it becomes easier to detect a difference, so power also increases. A meta-analysis is simply data pooled from several similar studies to come to an overall conclusion. This type of analysis achieves greater statistical power than individual studies. Meta-analyses are considered the highest form of clinical evidence, but they may be limited by the quality of the individual studies or bias in the studies selected for inclusion. The confidence interval is defined as the range of values in which a specified proportion of repeated sample means would be expected to fall. The 95% confidence interval most commonly used corresponds to a p-value of 0.05. The 95% confidence interval ranges from the mean minus 1.6 times the standard error of the mean to the mean plus 1.6 times the standard error of the mean. For a confidence interval of 99%, you use 2.58 as the multiplicative factor for the standard error of the mean instead of 1.96. More importantly, here are the practical applications of the confidence interval that should be remembered. If the 95% confidence interval for a mean difference between two variables includes 0, then there is no significant difference and the null hypothesis should not be rejected. If the 95% confidence interval for the odds ratio or the relative risk includes 1, then the null hypothesis is also not rejected. Finally, if the confidence interval between two groups overlaps, then these groups are not significantly different. It is fairly high yield to understand the differences between these three statistical tests. The t-test compares the means of two groups. For example, if you're comparing two cohorts based on systolic blood pressure means, use a t-test to determine whether there is a statistically significant difference. The ANOVA test compares the means of 3 or more groups. For example, if you're comparing 5 different cohorts based on systolic blood pressure means, use ANOVA to test for statistical significance. Basically, an ANOVA does the same thing as a t-test, but for a larger number of groups. Finally, the chi-square test compares 2 or more percentages or proportions of categorical outcomes rather than mean values. Use this test when dealing with categorical data that is represented as fractions or percentages. For example, the chi-square test would be useful for comparing the proportion of smokers with lung cancer versus the proportion of non-smokers with lung cancer. The correlation coefficient R, by definition, is always between -1 and +1. The closer the absolute value of R is to 1, the stronger the correlation between two variables, either in a positive or negative direction. Can you think of examples of both positive and negative correlations? If the correlation between stroke volume and cardiac output is 0.99, then there is a strong positive correlation between them. As stroke volume increases, cardiac output also increases. If the correlation between resistance and blood flow is -0.99, then there is a strong negative correlation between them. As resistance increases, blood flow decreases. The coefficient of determination is simply the square of the correlation coefficient. When used in the context of a statistical model like linear regression, it represents the proportion of variability in a dataset that is accounted for by the model. Values range from 0 to 1. The closer the value is to 1, the better the model fits the data. Turning to epidemiology now, let's discuss disease prevention. Disease prevention is divided into 3 tiers and can be remembered by the mnemonic PDR, which stands for Prevent, Detect, and Reduce Disability. Primary disease prevention is aimed at preventing disease occurrence to decrease both the incidence and the prevalence of disease. Can you think of examples of primary disease prevention? Examples of primary disease prevention include vaccines and hand washing. Secondary disease prevention is aimed at early detection of disease to decrease the severity of disease. Can you think of examples of secondary disease prevention? Examples of secondary disease prevention include screening tests, such as pap smears and colonoscopies. Tertiary disease prevention is aimed at reducing the morbidity and mortality stemming from the disease. Can you think of examples of tertiary disease prevention? Examples of tertiary disease prevention include most treatments, such as chemotherapy or surgery. Medicare and Medicaid are federal programs that originated from amendments to the Social Security Act. Medicare is available to patients over 65 years of age and to patients less than 65 years of age with certain disabilities and those with end-stage renal disease. There are 4 parts to Medicare. Medicare Part A covers inpatient care in the hospital, skilled nursing, hospice, and home health care. Medicare Part B covers outpatient care, doctor services, physical and occupational therapy. Medicare Part C covers a combination of Part A and B. Finally, Medicare Part D covers standalone prescription drug coverage. In comparison, Medicaid is federal and state health assistance for people with very low incomes. Again, you can remember that Medicare is for elderly and Medicaid is for the destitute.